So first of all, my name is Amir. I'm the VP of Research and Architecture here in DriveNet. Very, very happy to be here in the NFD for the second time. I'm doing that last year. If it's okay with you, let's roll. So what we're going to speak about now is the multi-service architecture from the technical perspective. I'm going to give you a little bit of recap about what we've been doing, what is the DriveNets architecture, and how we extend that toward what Ron just speak about before. Let's do it. So when we set out to do what we do, eventually we wanted to do something which is very, very different, to build a network operating system, which looks at the problem in a very different way than a classical incumbent vendor would have done it. We understand that this is the disaggregated problem. This is a distributed problem. Hence, the software needs to be disaggregated. Hence, the software needs to be distributed. It cannot be based on a monolith. So we took the compute resources, we took the networking resources, and thinking really hard, we understood that they're much more alike than different. I don't really care that the server does not have an NPU or that the white box has an NPU, but also has an x86 server. It's the secret sauce of the software to be able to utilize all of them at once and all of them optimally. And essentially, the DriveNets Network Operating System is much, much more than just doing the routing part, the management part. It's doing the virtualization part over both white boxes and servers. And of course, as Ron said, the DriveNets orchestrator, knowing how to utilize all of that, performance monitor all of that, and eventually put in the service on top of that, may it be the DriveNets one or anyone else. So when we originally came into this problem, what were the targets we set for ourselves? Essentially, built for any scale. I don't want to be complied into any specific scale. I don't care if it's 4 terabit or 200 terabits. I have to have my software linearly grow every time I'm adding a white box. More resources are added, more resources can be consumed. I have to grow like this, very much like cloud. I cannot be always confined into one CPU. I need to be operationally simple, meaning once deployed, I can take people that work on existing router for 20, 30 years and make the CLI look very different, like 10 sessions. I can't make it 10 times BGP speakers or many, many IGP entities. I have to make it look like a virtual chassis. And this is exactly what we've done. And another design target was I want it to be a single software. We're not in the era in which I can allow myself to have software for 10 clients or 100 clients, or in our case, 1 line card or 100 line card. It has to be the same software. It has to become an orchestration problem and not a software design problem. Hence, the use of microservices. And again, when we are coming into the network, it's not only bringing the DriveNets software technology, it's bringing the DriveNets view into how the network should look like. Simple, using the right technology, not have a million specific knobs that you can only use. So it's coming with that as well. It's more than just NOS. And then we'll look again at something that Ron said, just to bring up to the next set of slides. If you look at a monolithic chassis, you would usually have your control card, the route processor. In other company terminology, you would have the fabric engine, those line cards that are only in there to interconnect the actual network-facing line cards and the line cards themselves. The places in which you actually put the plugin, put the optics in, and connect either the customer or another networking device. What we've done is to take and first of all, disaggregate the hardware. This wasn't an easy part, and we had to take a lot of design decision, not only looking at what we were doing or what we are doing now, but also looking into the future. And we decided to disaggregate them into 2 building blocks: the NCP, the Network Cloud Processor or line card, and the NCF, the Network Cloud Fabric, the interconnection between these line cards. Even when you do something like that, there's a lot of engineering around it. How much capacity am I putting into the fabric? How much can I grow when the next line card comes? Do I have enough capacity in my backplane, not only for the service I'm running now, but for that I'm going to run 2 years from now? All of this got into this mixture of thought process we had to do here until we came out with this kind of resolution. And now we're going to spend a little bit of more time about what we were doing, what is in production, how we're doing it. So it's a lot of material, but I'll try to cover it relatively quickly. So going bottom up, as I said, I don't want to care about the exact platform. I want the controller to run the same way that the white box is running. I want the software stack to be coherent through and throughout. So going from bottom up, everything is running on top of Linux. The x86 of the white box, the x86 of the server, both of them are perfectly capable of running Linux. Then the platform and orchestration part. How am I speaking with that platform even before? There's a DriveNet software, there is DriveNet container. I need to orchestrate this device. What is the serial number? Where it's connected to? All of these are handled in this layer. And then this is the only place in which we bridge into the platform or the concrete chipset. The rest of the software is completely agnostic. When DriveNet says ACL or QoS policy, it's my representation of the world, my Yang module representing it. It's only in this layer where I do the translation between the DriveNet's world and let's call it the real world, regardless if the NPU is only for Broadcom or the platform is only from one ODM provider. Hardware abstraction layer, where I bridge into the translation, and then the Docker containers. On the control and management part, in a standalone box, this will be just poured onto the white box. If this is a cluster, a virtual chassis, this will run in pairs for redundancy. I have all the usual suspects to be run on management and control part. From the northbound interfaces, like a CLI, or Netcon, or SNMP, which is still used. All of them need to be battle-proven. Sometimes, it's kind of weird that it will sound, it takes you a lot of time to have your BGP perfect, but until every MIB works in the field, until every little trap is working at the field, you spend a lot of time. You have to battle-proven this kind of technology. syslog, accounting, RESTful API for automation, and gRPC. More precisely, GNMI, streaming telemetry, and we had the luck with our partners, with our customers, to push it beyond the extent that I would have believed to begin with. This would become the de facto standard right now. The configuration part, eventually you need to look at something that looks like a chassis or a facade of a chassis. You get your candidate configuration, you put configuration, an MTU, an ACL, you define a static route, you define a segment routing tunnel, an RSVP tunnel, and you commit, everything should work. You don't need to care if there's 50 machine here, 70 machine here. It's my problem, not yours. And that was the configuration part. The cluster management part. Is the box up? Is it functioning right? Are the lasers up? Do I need to do something? Is now the temperature crossing such a threshold that it's better for safety to take this platform down, causing a fast reroute? These are the type of information we're collecting in real time here and acting on. The operation management, the high availability policy. When you do so many elements, you can't have a global high availability view. You need to layer this problem. If a process crashes on a white box, let the white box handle it, send up an event. Now let me understand what I need to do. Do I need to ship control? Do I need to cause switchover? This is the way to act in layers and then act right and at the right time. Interfaces, statistics. We collect almost 1 million performance counters per second from each chip. I can't really export it out. I need to prioritize them. I need to zip them. I need to do logistics in order to take and extrapolate things like rate. All of this is done here. The routing protocols defined inside of Docker containers to give us flexibility to upgrade them. So these like BGP with all the different address families for unicast or multicast, IGPs like OSPF or ISIS working at scale, and of course tunneling or label distribution protocols like LDP and RSVP and segment routing, which is penetrating more and more and more into the market, in which we help a lot and which we support. Eventually, the RIB and the FIB, I need to distribute it onto all the line cards. Because of the architecture, the fact that the routing protocols are not limited by number of cores, the internal communication is very speedy. Our convergence time is amazing. Amazing because you have the compute to do it, you have the resources internally to do it, and it's on par, if not better, than anyone else.
We've got a quick question from Twitter. I wanted to jump in here. Kevin Myers is wondering, with regards to like a DDoS mitigation use case, assuming this is deployed in a scrubbing center, how rapidly can capacity be added to meet the demand of coordinated like DDoS attacks that you're basically being ransomed for? Can you bring that online quickly for massive volumetric attacks?
So you can do it very, very quickly. I think one of the interesting things that Kevin could ask himself is, why not to run the DDoS altogether to begin with on the router? And what you can do with that? Maybe the router can be the scrubbing center. So maybe a little bit food of thought, but try to think about it and you'll see when this type of architecture can take you. I agree with the question very, very much. And I think if you just look at it from a different perspective, maybe you'll see an even nicer solution here. So from WideWare perspective, software is running on top of that on the x86. Everything that I can handle locally is handled locally. So things like per port protocols like LACP or BFD, regardless if this is micro BFD or BFD for BGP, I'm assigning one of the NCPs and handling it in hardware. But even more complex things, if I need to collect or do flow monitoring, things like NetFlow, IPFix, instead of pushing it all into the controller, let's do it locally. Eventually a single packet will only come in one port. Therefore, I can collect it. After this, inside this white box, I can cache it inside this white box and I can export it inside this white box. And this is how you treat scale, localizing the problem again and again and again. And the fabric, very simple software, it's the same. The only place in which we're doing something more intriguing is if you have a massive scale of multicast replication, taking the fabric into account as a replication source. Now, if we're looking at the fully functional cluster, software deployed, this look like a single network entity, redundancy, everything you know, BGP nonstop routing, graceful restart. Everything works like the state-of-the-art router that you should work with. And this is all what we've already done. Now let's look into what we're doing right now and how did we get to this concept of multi-services. Essentially, what we are viewing from the market, not only us, is that we're in the beginning of a convergence period. A convergence in which the type of wired services, from one hand, wireless services requires an infrastructure. So I have EPC in 5G and BNG in wired. They need the same infrastructure to run upon. And this for us is a catalyst to view the network as something you converge, something you want to virtualize and give the same architecture through and throughout the different layers. So the transformation to network cloud is essentially based on a few things. The ability to optimally locate and place the network service, where it's not only can I serve the service, but it's becoming where should I serve the service. And in that aspect, this extends very well what we've already been doing with disaggregation, what we've been doing with cloud native technology. I need one software stack for multiple network use cases. The VPNs, the mobility, the internet peering. I need to quickly adjust to different network needs. If I need more capacity, I need a new technology. I need a different tweak to a protocol. Let's deploy it. And that allows us as DriveNet to bring very high feature velocity. And also all of this comes only with a single operational pane of glass. I need to stream it. I need to probe it. I need to bring all of this information into a single place to take decision. If yesterday decision was whether does it work or not, tomorrow it's going to be how am I influencing the service because of what I'm seeing. So let's take the current central office and see what we can do with it, with a line of thought like I'm trying to convey here. In most service providers, if we look at a CO, we would see the PEs, the provider edge. This is the service attachment point. For example, internet peering, mobility services, enterprise services like layer 2, layer 3, VPNs. These are distinct routers for two reasons. One, you bought them. You bought a specific machine, which is very, very good and doing a specific function. Second, you have a different operational environment, a different operational team. There's the guys who look at the VPN CLI, there are the guys who look at the internet CLI for a reason. There's a difference in the way you maintain them. There's a difference in the way you can operate them, act in case of failure. And then you have your core device, which is roughly half and half on a good day. Half is really interconnecting between cities, and the other one would be best set as just an interconnectivity metrics. How you interconnect the PEs within a site. And you pay a lot of money to do something like that. So through and throughout, we see inefficiencies. Now, Let's bring a little bit of thought. Came in COVID-19. People moved from working at the enterprise to work at home. All the capacity shifted to home. What happened to your port on your VPN router? How could you have repurposed it? You can't. Regardless if it was up or down, there was no way to take the ability on that line card in the VPN router and make it used as an internet router. And for me, it's just mind-blowing. And isn't that exactly what virtualization is coming to solve? This roaming of bandwidth, this roaming of resources. So what we are doing, we are going to a very, very different model. I'm taking the cluster, and I don't want to speak at a line card level. I don't want to speak in a way that's limits you, that this can be only connected here and that can be only connected there. I want every port to be able to connect anywhere and to attach to any service. Let me have the problem of where do I allocate the internal resource? Yeah, it's kind of interesting. There's a lot of engineering behind it, but let's look at what I'm gaining. I don't want to know what the port is connected to. In this case, if I have, again, the business services, layer 2, layer 3 VPN, the internet edge, the mobility service, connect them everywhere to each and every one of the line cards. And I will make sure all of them works. What does it give you? Full flexibility. Now you grow in a cluster form, in a pod form, without knowing where you're going to invest the next port. So if we look again at what we bring at the cluster level, the same base OS, the same platform and orchestration, and now let's differentiate the infrastructure part. It will be there not only to run a service, but as a vessel to run a multitude of services. Now let's deploy the services. It's not only one. If we've been doing core routing as a use case, peering as a service, now let's do them all at once. So if I'll change or tweak a little bit my design guidelines, now it's built for any scale and any service. It's designed for operational simplicity, but at 2 layers, the infrastructure layer and the service layer. It's a single infrastructure and service experience. You should look at the infrastructure, you should look at any service and get the same look and feel. And it should be fully flexible. There is no more limitation at the port level, line card level. A little bit of terminology. Now the application would be termed a service instance. A service instance is the virtual router, if you want. You get reserved resources, x86 cores, data plane resources, ACL, route entries, whatever you can think about, QS policies. This is where your control plane is running. You have a BGP in the context of this SI, BGP for VPN. Another SI would be internet peering. It has its own version of BGP. They can run a different version because most likely in network, that's what you're doing. Data plane software is running within this context. This is where you attach the physical and logical port, the VLAN, the physical port, whatever you want is a network interface. And they're virtually unaware of one another, like VMs in the cloud, like different container or Kubernetes pods in the cloud, which is essentially the most or the strongest kind of requirement here. To interconnect them, we've created a virtual link, which we call an inter-service link. This allows for control plane to go between them, service to be chained. And even though it's virtual, and as I'll speak shortly, it's running over the fabric and not with external ports, we present it as a link which you're already familiar with. So quality of service policies are applied to, ACL can be applied for security, protocols are running on, and you measure it. You have performance counter as if you're looking at a physical cable. But why using the fabric? 1, we have the capacity. 2, you don't need to recable it. 3, you take down power consumption a lot. The fabric machines are not doing deep packet inspection. They don't do complex packet processing. So the power they draw is much, much lower than going between physical routers. What do you get with that? Now you get virtual routers running on top of DriveNets cluster. You have your virtual control plane for the mobile service. You get your virtual control and management plane for the business services and so on and so forth. And I, at the hypervisor layer, will speak about know where to put the data plane resource. You can connect anywhere. I know where to use the NPU, how much to use of the NPU to give you this effect. So what is the software architecture we came up with? Very similar to what we started with, which is a great kind of benefit, a great kind of evidence that what we started with is already nice. So we better differentiate what is infrastructure, what is service. I look at the DNOS part and start bottom up. Hardware is the same, backward compatible. The cluster management part remain the same. x86 virtualization, Docker containers, virtual machines, container network function, NPU virtualization. Now you're not speaking with the actual TCAM or the actual feed. You're speaking with my virtual representation of it. It's the function of the hypervisor to do the translation between what you think you see and what's in reality there. The Network Cloud API, in which you work directly or indirectly, and then the service instances or the feature. SI1 would be a VPN router. SI2 would be an internet peering. SI3 would be a core router. Why can we do it? So Ron touched it a little bit, but the interesting thing when going deep into understanding how different routers operate is to understand that they're balanced on different resources. You could have a lot of ports and the router would be never utilized that much because something else was already scarce. So if we take a core router, for example, what's interesting to a core router or an aggregation router is almost usually the sheer bandwidth, the number of ports I'm using. But from other aspect, there is not a lot of BGP peering going on. The QoS policies are relatively lean. The route scale, usually it's an MPLS device, meaning that you're doing label switching or label insertion. You're not utilizing TCAM resources so much, and we have a large TCAM on the DriveNets devices. Therefore, a lot of the other resources are free. If we look at a VPN service, on the other hand, completely off balance, differently balanced. A lot of compute resources are used. I have a lot of VRFs. I'm doing BGP in the context of these VRFs with customers. I have a lot of route entries in the context of a VRF. And I have rich QoS policy in the context of what subrating I'm doing with this customer, and so on and so forth. So they're complementing one another. Internet peering would be very much the same. So what we see here is that we have different attributes. If I compare it to something in compute, it's like having a compute program which runs for a long time, doing a complex kind of computation, needs a lot of resources, but is not delay sensitive. And then you have another smaller application who needs to come in and out for a shorter compute, but it's very delay sensitive. In that essence, they're complementing one another. So what the DriveNets cluster gets you to? Let's look or envision three types of services. I would have my yellow service here. It would require, for the benefit of the debate, 4 terabit per second, but it needs the entire TCAM, the gigantic TCAM on this machine. This would be, for example, a VPN service. I'll take another two services of choice. One would be the orange one, let's say internet peering, which needs 200% of rate, like 8 terabit per second, and 50% of the TCAM. Let's say it's the internet table, we can do it with much less, but just for example's sake. And the blue one would be, for example, a short uplink or something like a core device. Now I want to orchestrate all of them into the machine, and the target function, any port could be connected anywhere. So what the hypervisor is doing, the internal orchestrator is doing, is to ask, where do I have the resource? Can I place the yellow function on a single line card or 2 line cards for redundancy? Let's put them there. Where can I put the orange service and the yellow service? They can live together on the same line card. Let's put them together on 2 line cards. What happened? How am I enabling the customer to still have, in this case, a yellow port on whatever line card? He connects it, and when the packet comes in, I ask myself one question: can I treat it or not? And if the answer is not, now I'm not solving for the next hop. I'm solving for the next line card. I'm going through the fabric as if I'm going through a physical cable within routers, and now I solve it. So this is like implementing 2 physical routers onto the same device. And I hope that the type of reduction in cost, the type of reduction in power, the type of enablement that this kind of technology bring into our network industry is clear. Now, instead of cabling more and more routers, we can bring more and more services. To summarize, in order to do service instant cloudification, we needed to define three things. Any port can be used. I don't want to be tied into a physical function like a router or a line card. Any port can be used. I want to be able to do optimal service placement. I look not at the local problem, just the VPN, just the internet, just whatever. I want to do global optimization, and I need to have an efficient inter-service connection. Power efficient, time efficient, and efficient in terms of enabling you to roam this traffic, even internally, by change of configuration and not by change of cabling. So DriveNets is pushing this through and throughout. DriveNets is pushing this with all the power we have, just from the fact that personally, we really, really believe it.
We actually got another one from Kevin Myers. How much of the push to move content delivery network content into the last mile is driving the adoption of scalable fabrics into central offices that have traditionally been dominated by more of the fixed chassis telco oriented solutions? Do you guys see CDNs as being a driver for a lot of the changes that are being made?
So I think, first of all, it's an excellent question. I think CDN, it's one of the catalysts, and it has a lot of sense because instead of having very large CDN sites, now you can have probably something of a smaller CDN site with the location of the router. But I think this kind of problem could be extended not only for CDN, but for anything that can benefit from proximity to the customer. If we change the name CDN with something else like steering traffic, like DDoS, you would see that whatever has benefit of being in the context of being close to the customer, serving a smaller portion of the traffic, and being able to do that, coexisting or co-locating with other services, I think this is not only the way to go, this is the only way that scaling networking could work with.